Hello dear students. Today we are going to start with thermodynamics part 4. The thermodynamic property that we shall be talking about today is heat. Heat, what does heat do to you? It increases your temperature, it increases your randomness, it increases your restlessness. Most of the people don't actually enjoy the too much heat. So the same thing we are going to discuss here. What is heat? You've done in physics, a form of energy. What form of energy is what we are going to elaborate on today. Heat is a form of energy which tends to flow from one body to the other when there is a temperature difference between them. So, for example, we have two objects here, A and B. One is at a temperature of 25 degrees Celsius, the other is at 35 degrees Celsius. If the two are connected by a conducting wire, we notice that heat flows from B to A till an equilibrium is established. Equilibrium means the heat still continues to flow in between the two objects, but the temperature then becomes constant. Initially, you will find that the temperature of B begins to decrease, that of A begins to rise. But once equilibrium is reached, they reach a constant temperature state, and that is an equilibrium state. So heat is a form of energy which flows between two objects connected to each other when there is a difference in temperature between them. Heat and work, we had earlier done work in part 3 video. What is work? We said it's something which is used to either expand or contract, because we talked about the work of expansion and contraction under thermodynamics under gases. If you do work on a gas in a container, you do work means the pressure or the work is being done by the surroundings. In such a scenario, you will actually be pushing the piston down and you will be bringing the particles closer to each other. On the other hand, if this same gas is heated, we are not applying pressure, we heat the gas. In that case, we notice that the movement of particles increases and they have a tendency to push the piston out unless the pressure is maintained as constant. So if you realize when work is done on the system, it helps to organize it. It helps to bring the particles closer. When heat is applied on a system, it causes the system to become more random. The particles tend to fly apart. They move away from each other because of the energy given to them. So we say heat is a more random form of energy, work is a more organized form of energy. Both are forms of energy but having different effect. We represent heat by either a small q or a capital Q. We know that since it is a form of energy, it will have the unit either joule or erg depending upon what system of units you are using. As I said earlier, we shall be building on the concepts that you already know. Now in physics, you would have read that heat is directly proportional to the difference in temperature. Very simple. You have to heat water from 10 degrees Celsius to 100 degrees Celsius. Or you have to heat water from 10 degrees Celsius to 20 degrees Celsius, considering that the mass of water remains the same. In which case will you have to apply more heat? The first, where the rise in temperature is 100 minus 10, that is 90. Or second, where the rise in temperature is simply 20 minus 10, that is 10 degrees Celsius. Obviously, more the temperature difference, more is the amount of heat required. So Q is directly proportional to the difference in temperature. Because we are talking about difference in temperature, we can say in Celsius or Kelvin, the magnitude, the physical value remains the same. Amount of heat also varies directly as the mass of substance taken. So I have to heat 1 gram of water by 1 degree Celsius and I have to heat 1 kilogram of water by 1 degree Celsius, in which case will the amount of heat required be more? Yes, 1 kilogram, or alternately if you want to state its volume, we'll say 1 liter of water will need more amount of heat. So that means the amount of heat required directly varies as the mass of substance taken. Combining the two factors, we have heat is directly proportional to the mass of the substance taken into the difference in temperature. Removing the proportionality sign, we put a constant here which is known as specific heat capacity. Now why are we calling it as specific heat capacity? I'll explain in the next step. C is Q upon M into delta T, because we need to define this C. Very simple way of defining is you define the denominators as 1. So if I'm taking 1 gram of the substance and the temperature is change in temperature is 1 degree Celsius or 1 Kelvin, this C, specific heat capacity, becomes equal to Q. So we define it as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. If you notice over here, we are defining the mass as 1 gram. We are talking about a specific mass of the substance. Hence the term specific heat capacity. If on the other hand, I do not consider mass as 1, then in that case, you will have mass multiplied by the specific heat capacity gives us what we call as heat capacity. The difference in the two is, when you define heat capacity, it will be amount of heat required to raise the temperature of, that's it, this disappears, of a substance by 1 degree Celsius. As simple as that. If you recall in physics also, you do it as Q is equals to mc theta. It's one and the same thing. Only thing is the terms that we are using are different. The symbols that we are using, it is effectively the same. So according to the IUPAC, specific word is used when you're talking about a fixed mass, a specific mass of the substance, and that's usually a unit mass. Now when I talk about unit mass, now that mass in chemistry, we deal with moles. A mole of a substance more often than a gram. So we have also introduced a new term called as molar heat capacity. So instead of specific, it becomes molar heat capacity. Now molar would be amount of heat required to raise the temperature, or you can also say change the temperature of 1 mole of a substance by 1 degree Celsius. As simple as that. And in such a case, what do is we put a bracket M. So when I will say Cp, I have here C specific heat capacity. I will put a small m as the subscript, indicating that we are talking about molar specific heat capacity. C, that is specific heat capacity, is a specific or a characteristic value of a substance. Like water has a very high specific heat capacity, indicating that you need a large amount of heat in order to change its temperature by 1 degree Celsius. When we talk about gases, we know that gases behavior is affected by change in pressure as well as change in volume. Hence, we need to further expand our definition to include these two factors of pressure and volume. So, we introduce Cp and Cv. The subscript here indicates what is remaining constant. So, when I say Cp, that is specific heat at constant pressure, Cv, specific heat at constant volume. The value still remains the same, amount of heat required to raise the temperature of 1 gram of a gas by 1 degree Celsius at constant pressure or at constant volume. That's the only difference that you will make. Now, when I'm talking about specific heat, we shall write the C over here as a small c, whereas if I'm talking about only the heat capacity At constant pressure or constant volume, we denote it by a capital T. That is the only difference, but you have to be careful. Let us now see the units for each of them. Q, as we know, is represented by joule. Mass, when I am talking about specific heat capacity, so I have joule, mass is in gram, temperature either degree Celsius or Kelvin, whatever you may like, or whatever is the requirement of the question, because we are talking about change over here. So it is joule per gram per Kelvin or joule per kilogram per Kelvin, depending upon the unit that you are using. Same way, heat capacity on the other hand. Now here we are not talking about per gram. So the unit for heat capacity simply becomes joule per Kelvin. How much heat is required to change the temperature of a substance by 1 degree Celsius? Simple. Again, we come back to specific heat at constant pressure, constant volume. Only thing is the factors are remaining constant. Looking at the overall picture, we know that heat depends on the mass of the substance taken. In the first video, we had discussed about extensive and intensive property. A property which is depending upon the amount of substance taken is an extensive property. So heat is an extensive property. But if you are asked specifically specific heat, now specific heat is per gram. So specific heat would be an intensive property, a property which is independent of the mass of substance taken. Heat also varies with the conditions of the reaction. So we have Cp, specific heat at constant pressure. We have Cv, specific heat at constant volume. Hence we say heat is a path function depending upon the path taken to bring about that change. Further on, as we go ahead in our derivations, in further videos, we shall be deriving the relation between Cp and Cv, which for now you can just remember as Cp minus Cv is R. It's a universal gas constant 8.314 joule per mole per Kelvin. It's the amount of work done when the temperature of 1 mole of a gas is increased by 1 degree Celsius or 1 Kelvin. Please remember, when you're talking about difference in temperature, whether it is Celsius or Kelvin, it is the same. The ratio of the two, Cp upon Cv, is denoted by the symbol gamma, known as the Poisson constant. We shall be discussing more about these in our further videos and extending our concept in order to derive a relation between the three thermodynamic quantities that we have learned till now: internal energy, work and heat. Before you go on to part 5, I would request you to first go through part 1, 2, 3 and 4 and make your understanding clear, and be ready for part 5, where we shall introduce the first law of thermodynamics. I shall await your feedback. Have a good day.